What if everything that exists does not end where our ability to see ends? For centuries, humanity imagined that the universe was far smaller than it really is. First, there were the stars visible to the naked eye. Then telescopes revealed that many of those tiny points of light were distant worlds, and that our own galaxy contained hundreds of billions of stars. But then we discovered something even more unsettling. The Milky Way was not the universe. It was merely one galaxy among hundreds of billions of others. And as our instruments began looking farther and farther into space, they encountered a boundary that was not made of matter, nor a wall, nor even an empty region of space. It was a boundary created by the very nature of light. We call it the observable universe. It is the region of the cosmos whose light has had enough time to reach us since the beginning of cosmic expansion. Its scale is almost impossible to comprehend. The observable universe is roughly 93 billion light-years across. But this is where the real question begins. What lies beyond it? Because those 93 billion light-years do not necessarily represent the total size of the universe. They represent only how far we can receive information from. That distinction is fundamental. When we observe a galaxy billions of light-years away, we are not seeing it as it exists today. We are seeing it as it was when its light began its journey toward us. The farther we look, the farther back in time we see. And the deeper we look, the closer we come to an era when the universe was young, incredibly hot, and far denser than it is today. But there is a limit. There are regions of the cosmos whose light simply has not had enough time to reach us. And there may be others whose light will never reach us. That means that while our telescopes search the sky for the oldest signals in the universe, an enormous reality may exist beyond our observable horizon, a reality containing galaxies, clusters, stars, and structures that we may never be able to detect directly. Not because our telescopes are powerful enough, but because the fabric of space-time itself may prevent us from ever receiving that information. And this leads to one of the most unsettling ideas in modern cosmology. The universe we can observe may be only a tiny region of something vastly larger. But what does beyond actually mean? Are we talking about space that simply continues forever? Is there a physical boundary beyond which absolutely nothing exists? Could the universe be finite, yet have no edge? And what does the expansion of space tell us about everything we may never be able to observe? Even more importantly, if a region is forever beyond our reach, how could we ever know that it exists? The answer is not as simple as it might seem. Because in cosmology, there is an enormous difference between what we can observe, what we can infer, and what we can merely imagine. Understanding that difference will be essential to answering the question at the heart of this journey. What is really beyond the observable universe? To find out, we first need to go back to the moment when scientists realized that the universe was not static. Because that discovery would forever change our understanding of the cosmic horizon. For most of human history, the universe appeared almost completely unchanging. The stars rose and set with remarkable regularity. The planets moved across the sky in predictable patterns. And beyond them, the distant stars seemed fixed against an eternal cosmic background. Even after astronomy became a precise science, the prevailing assumption was that the universe itself was essentially static. That began to change in the early 20th century. Albert Einstein's theory of general relativity had revealed something extraordinary. Space and time were not merely a passive stage on which the universe existed. They were dynamic. Matter and energy could influence the geometry of space-time itself. Einstein's original equations, however, seemed to suggest something uncomfortable. A universe containing matter should not naturally remain perfectly static. Gravity should cause it to evolve. To maintain a static cosmos, Einstein introduced an additional term into his equations, the cosmological constant. At the time, the idea of an expanding universe seemed almost absurd. Then astronomers began looking farther into space. Edwin Hubble and other researchers discovered that many objects previously thought to be part of the Milky Way were actually enormous galaxies far beyond it. the universe suddenly became vastly larger. But the most important discovery was still to come. When astronomers measured the light from distant galaxies, they found that the wavelength of that light had been stretched toward the red end of the spectrum. This phenomenon is known as cosmological redshift. The farther away many galaxies appeared to be, the faster they seemed to be moving away from us. It was not simply that galaxies were flying through some pre-existing empty space. The space between large-scale structures was itself expanding. This relationship became known as Hubble's law. On average, the more distant a galaxy is, the faster its distance from us increases because of cosmic expansion. The implication was profound. If the universe is expanding today, then in the past it must have been smaller, denser, and hotter. Run the cosmic clock backward far enough, and the universe approaches an extremely hot, dense early state. This became the foundation of what we now call the Big Bang model. But there is an important misconception to eliminate. The Big Bang was not an explosion occurring at one particular location in empty space. According to modern cosmology, space itself was expanding. There was no ordinary center from which galaxies were thrown outward into pre-existing darkness. Every large-scale region of space participated in the expansion. A useful analogy is the surface of an inflating balloon. Imagine galaxies drawn across its surface. As the balloon expands, every galaxy sees other galaxies moving away from it. There is no special point on the surface that acts as the center of the expansion. The analogy is not perfect, because the real universe has 3 dimensions of space rather than the 2-dimensional surface of a balloon. But it helps illustrate one crucial idea. The expansion happens everywhere. And this changes the meaning of distance. Light does not travel through a completely static universe. As photons cross the cosmos, the space between their source and their destination can expand. A photon may begin its journey when 2 galaxies are relatively close together, yet arrive after billions of years when the distance between those regions of space has become enormously larger. This is one reason why the observable universe can be much larger than the simple calculation of the universe's age multiplied by the speed of light. The universe is approximately 13.8 billion years old. You might therefore expect the farthest observable objects to be around 13.8 billion light-years away. But the expansion of space changes the calculation. The regions that emitted the oldest light we can detect are now much farther away from us than they were when that light began its journey. And eventually, cosmologists encountered another remarkable discovery. The expansion of the universe is not merely continuing. It is accelerating. Observations of distant type Ia supernovae in the late 1990s provided strong evidence for this acceleration. Something was causing the expansion of the universe to speed up over cosmic time. Scientists call the unknown component responsible for this effect dark energy. We still do not know what dark energy fundamentally is. It could be related to the energy of empty space. It could point toward new physics. Or our understanding of gravity on the largest scales may be incomplete. But whatever its nature, cosmic acceleration has enormous consequences for the question we are investigating. Because if space continues expanding at an accelerating rate, some distant regions of the universe are becoming increasingly isolated from us. Their light can be traveling in our direction while the expansion of space between us changes the distance faster than the light can compensate. Eventually, a boundary emerges. Not necessarily a physical boundary in space. A cosmic horizon. Beyond that horizon, events may be forever inaccessible to us. And this is where the story becomes much stranger. Because the observable universe is not a permanent sphere surrounding Earth. As time passes, the region from which light has had enough time to reach us can change. At the same time, accelerated expansion can create regions from which signals emitted today will never reach us. So there are actually different concepts hidden behind the simple phrase, the edge of the universe. There is the limit imposed by the finite age of the cosmos. There is the distance to the oldest light we can observe. And there is a future horizon determined by the expansion of space itself. These horizons are not walls. They are consequences of space-time, light, and cosmic history. And that leads to an extraordinary possibility. Some of the galaxies we can see today may already be permanently beyond our future reach. We can receive their ancient light because it began traveling toward us long ago. But any new light they emit now may never arrive. In other words, we may be watching the final chapters of objects that are, in a cosmic sense, already disappearing beyond our horizon. Yet all of this raises an even deeper question. If we cannot see beyond the observable universe, how can cosmologists say anything meaningful about what might exist there? The answer comes from one of the most powerful ideas in modern science. We do not need to observe an entire system directly to understand its underlying laws. And the evidence for what lies beyond our cosmic horizon may already be encoded in the universe we can see. To understand what may exist beyond the observable universe, we first need to understand what the observable universe actually is. The phrase sounds simple. But scientifically, it describes something much more subtle than a giant sphere with a visible edge. The observable universe is defined by information. Specifically, it is the region of space-time from which signals have had the opportunity to reach us since the early universe. And the most important signal of all is light. Light travels through space at approximately 300,000 kilometers per second. That speed is extraordinarily fast by everyday standards, but the universe is so vast that even light requires billions of years to cross cosmic distances. The light from the Sun takes about 8 minutes to reach Earth. The light from the nearest star beyond the Sun takes more than 4 years. Light from distant galaxies can spend billions of years traveling through the cosmos before reaching our telescopes. This creates a fundamental limitation. We cannot see an object as it exists at the present moment if its light has not yet had time to reach us. Astronomy is therefore also a form of time travel. Every telescope is looking into the past. The deeper we look into space, the further back in cosmic history we see. And eventually, we reach an extraordinary limit. The universe became transparent. In its earliest stages, the cosmos was filled with an extremely hot plasma containing charged particles that constantly interacted with photons. Light could not travel freely across enormous distances because it was repeatedly scattered. The universe was, in a very real sense, opaque. Then, roughly 380,000 years after the beginning of cosmic expansion, the universe had cooled enough for electrons and atomic nuclei to combine and form neutral atoms. Photons were suddenly able to travel much more freely. Those ancient photons have been moving through the universe ever since. Today, we detect them as the cosmic microwave background, or CMB. The CMB is not the beginning of the universe itself. It is the oldest electromagnetic light that can be observed directly. And it provides an extraordinary snapshot of the universe when it was only a fraction of its current age. When scientists map the CMB, they find tiny variations in temperature across the sky. These variations are incredibly small, but they are enormously important. They represent slight differences in the density of matter in the early universe. Over billions of years, gravity amplified those tiny differences. Regions that were slightly denser attracted more matter. Matter gathered into enormous structures. Galaxies formed. Galaxies gathered into groups and clusters. Clusters became connected by vast cosmic filaments. And between them developed immense cosmic voids. The large-scale structure of the universe therefore carries information about conditions that existed billions of years ago. But what does any of this tell us about regions we cannot observe? The key is a principle known as the cosmological principle. On sufficiently large scales, the universe appears to be approximately homogeneous and isotropic. In simpler terms, if we zoom out far enough, the universe does not appear to have a special central region or an obvious preferred direction. That does not mean every part of the universe is identical. Stars form in some places and not others. Galaxies collide. Clusters contain enormous concentrations of matter. But when averaged over sufficiently large scales, the distribution of matter becomes remarkably uniform. This observation gives cosmologists a reason to believe that the region beyond our observable horizon may follow the same physical laws as the region we can observe. Notice the wording. It is not proof. We cannot directly inspect an unreachable region. Instead, it is an inference based on the evidence available to us. And that distinction is essential. Science can make powerful predictions about things that cannot be directly observed, but those predictions depend on models, assumptions, and evidence. There is another important concept here: cosmic inflation. According to the inflationary model, the very early universe underwent an extraordinarily rapid period of expansion. Inflation was proposed to explain several otherwise puzzling features of the cosmos, including its remarkable large-scale uniformity and its near-flat geometry. If inflation occurred, then the portion of the universe we can observe today could represent only a tiny patch of a much larger cosmic region. Imagine taking a small section of an enormous curved surface and zooming in until it appears almost perfectly flat. From that limited perspective, you might conclude that the entire surface is flat. But the larger structure could extend far beyond your field of view. Something similar may be happening on cosmic scales. Our observable universe could be so small compared with the total universe that its geometry appears almost perfectly flat, even if the universe as a whole has a more complicated global structure. Measurements of the cosmic microwave background strongly indicate that the observable universe is very close to spatially flat. But flat does not necessarily mean infinite. This is another common misunderstanding. A universe can be spatially flat and still be finite, depending on its global topology. For example, a hypothetical universe could have a geometry in which traveling far enough in one direction eventually brings you back to where you started, without encountering an edge. The three-dimensional equivalent is difficult to visualize, but mathematically such possibilities exist. So when scientists say that the observable universe appears flat, they are not automatically saying that the entire universe must extend infinitely in every direction. The observations simply constrain the possible geometries and sizes. And there is yet another complication. The universe is not merely expanding. Its expansion is accelerating. This means that there are regions whose present-day light may never reach us, regardless of how long we wait. To understand why, imagine sending a photon toward Earth from an extremely distant galaxy. The photon moves through space at the speed of light. But the space between the photon and Earth is also expanding. If cosmic expansion is sufficiently rapid over the relevant distances, the photon can continue traveling toward us while the overall distance to its destination grows in a way that prevents it from ever arriving. This does not mean that the photon locally violates the speed of light. It is not moving through space faster than light. Rather, the geometry of spacetime itself is evolving. This produces what cosmologists call a cosmic event horizon. It represents a boundary beyond which events occurring now may never be able to influence us in the future. And this is profoundly different from the observable horizon. The observable horizon asks, what signals have had enough time to reach us? The event horizon asks, what signals emitted from a distant region will ever be able to reach us, even given an unlimited amount of time? Those are not the same question. Some objects can therefore be observable today while remaining outside our ultimate communication range. We can see their ancient past, but we may never be able to receive their future. This is one of the strangest consequences of an expanding universe. The cosmos does not simply become bigger. It changes what parts of itself can ever be connected by information. And that brings us to the central mystery. If the laws of physics appear to operate consistently throughout the region we can observe, and if the universe looks remarkably uniform on the largest scales, then the simplest assumption is that the universe continues beyond our observable horizon. There may be more galaxies, more dark matter, more cosmic voids, more clusters, perhaps even structures vastly larger than anything we can see. But there is a limit to what science can claim. We do not currently have direct observations of what lies beyond the observable universe. Everything beyond that boundary belongs to the realm of inference. And the deeper we investigate, the more uncomfortable the question becomes. Because if the universe continues beyond our horizon, how far does it continue? Does it end somewhere? Does it continue forever? Could the entire cosmos have a finite volume? Could inflation have created regions so vast that our observable universe is merely one tiny patch among many? And if so, is there any possible observation that could distinguish these possibilities? These questions lead directly into the territory where cosmology becomes most fascinating. Because beyond the edge of what we can observe lies not simply darkness. It lies the boundary between what the universe may contain and what the universe may never allow us to know. At this point, we can separate the mystery from what science has actually established. We know the universe is expanding. We know that expansion has changed throughout cosmic history. We know that the observable universe extends far beyond the distance light could have traveled through a static 13.8 billion-year-old cosmos. We know that the universe contains an enormous variety of structures, from individual galaxies to immense clusters and vast cosmic voids. And we know that the portion we can observe represents only the region from which information has been able to reach us. But there is one fact that is easy to overlook. We do not know the total size of the universe. It could be enormously larger than the observable universe. It could be finite. Or it could be infinite. Current observations have not established which of these possibilities is correct. This may sound surprising. After all, modern cosmology can measure the age of the universe, estimate the amount of ordinary matter and dark matter, reconstruct its expansion history, and map the cosmic microwave background with extraordinary precision. Yet the total size of the cosmos remains unknown. The reason is fundamental. A telescope can only observe information that reaches it. If there is a region beyond our cosmic horizon whose signals cannot reach Earth, no improvement in telescope technology can simply reveal it. The problem is not sensitivity. It is causality. Information cannot arrive from a region that is permanently disconnected from us. And this is why the word observable is so important. The observable universe is not necessarily the universe itself. It is the part of the universe that is accessible to our observations from our particular location in space-time. An observer somewhere else in the cosmos would have their own observable universe. Their cosmic horizon would overlap with ours, but it would not necessarily be identical. This means there is no universal sphere surrounding the entire universe with Earth sitting at its center. We are at the center of our own observable universe simply because every direction we look is measured outward from our location. An observer in a galaxy billions of light-years away would also find themselves at the center of their own observable universe. There is no contradiction. The horizon is observational, not physical. And this distinction helps explain one of the most important pieces of evidence we have about the large-scale universe. The cosmic microwave background appears remarkably uniform across the sky. Its temperature is approximately 2.7 Kelvin, with tiny fluctuations that encode the seeds of later cosmic structure. These fluctuations have been studied in extraordinary detail. They tell us about the early universe's density variations, its composition, its geometry, and the history of its expansion. They also provide constraints on how large the observable region could be and how the universe may extend beyond it. So far, the evidence is consistent with a universe that is extremely close to spatially flat on observable scales. But again, flatness does not answer the question of whether the universe is infinite. To understand why, imagine a tiny creature living on a gigantic surface. If that creature could see only a small patch around itself, the surface might appear completely flat. Only after traveling across an enormous distance could it potentially detect the surface's global curvature. The same basic principle applies to cosmology. If the total universe is vastly larger than the region we can observe, any global curvature could be so weak that detecting it would require measurements far beyond our current horizon. So when cosmologists say that the universe is flat, they are describing the geometry we can measure. They are not necessarily describing the global shape of all existence. There is another major piece of the puzzle, the distribution of galaxies. On relatively small scales, the universe is highly structured. Galaxies form groups and clusters. Clusters are connected by filaments. Immense voids separate the densest regions. But when viewed across sufficiently enormous distances, these variations average out. The universe becomes statistically homogeneous and isotropic. This is consistent with the idea that what lies beyond our observable horizon may resemble what lies within it. If the universe follows the same large-scale rules everywhere, then beyond our horizon there should not suddenly be a mysterious cosmic wall. Instead, there may simply be more universe, more regions of space, more matter, more dark matter, more galaxies, more cosmic history unfolding beyond our ability to observe it. But this is where an important distinction must be made. The phrase, "there is probably more universe beyond the observable universe," is scientifically reasonable. The claim we know exactly what is there is not. We don't. Our observations constrain models. They do not provide a direct photograph of unreachable regions. And even the best supported models contain unknowns. Dark matter remains unidentified. Dark energy remains unexplained at a fundamental level. The physics of the earliest moments of the universe is incomplete. And we still do not possess a fully established theory that unifies general relativity with quantum mechanics. These gaps matter because our understanding of the universe beyond the observable horizon ultimately depends on how accurately our physical theories describe reality on scales and conditions we cannot directly test. There is, however, something else we can investigate. The universe contains patterns that extend across enormous scales. The cosmic microwave background, galaxy clustering, gravitational lensing, baryon acoustic oscillations, and the expansion history all provide independent pieces of evidence. When these observations are combined, they produce a remarkably successful description of the observable cosmos. This model is often called the lambda-CDM model. In broad terms, it describes a universe dominated by dark energy and dark matter, with ordinary matter making up only a relatively small fraction of the total cosmic energy budget. It has successfully explained a vast range of observations. But successful does not mean complete. The model tells us how the universe behaves on the scales we can study. It does not necessarily reveal what the universe ultimately is. And there is an even deeper limitation. Our observations are always made from inside the universe. We cannot step outside the cosmos and photograph it from the exterior. There is no known external vantage point from which we could simply look back and see the universe as a whole. We are embedded within the system we are trying to understand. That makes cosmology fundamentally different from many other sciences. We cannot place the universe inside a laboratory. We cannot perform controlled experiments on the entire cosmos. Instead, we observe its history, measure its present state, construct mathematical models, and compare those models against the evidence. And so far, those observations give us a fascinating but incomplete picture. The observable universe appears remarkably uniform on the largest scales. Its geometry is extremely close to flat. Its expansion is accelerating. Its early history is encoded in ancient radiation. And the laws of physics appear to work consistently throughout every region we can test. All of this makes one possibility especially compelling. There may simply be more universe beyond the horizon. But more universe is still a phrase hiding a gigantic unknown. How much more? A little? A trillion times larger? Infinitely larger? And could there be something fundamentally different beyond the region we can observe? At present, we cannot directly answer those questions. Yet there is a reason scientists continue to investigate them. Because the universe has already surprised us before. The discovery that galaxies exist far beyond the Milky Way transformed our understanding of reality. The discovery of cosmic expansion transformed it again. The discovery of accelerated expansion introduced an entirely unknown component into the cosmic equation. And now, the observable horizon confronts us with perhaps the most difficult question of all. What if the part of the universe we can see is not representative of the whole? That possibility leads us toward the central mystery. Because perhaps the greatest mystery is not what exists beyond our horizon. Perhaps it is whether the laws and conditions we observe here continue indefinitely beyond it. And if they do not, we may have no way of knowing. There is a strange moment in cosmology when the equations continue to work, but our intuition stops working. We can calculate the age of the universe. We can reconstruct its expansion. We can detect light that has traveled for more than 13 billion years. We can measure tiny fluctuations left over from the early cosmos. And yet, when we ask the simplest possible question, what is beyond the observable universe? We reach a boundary where direct knowledge ends. Not because scientists have stopped looking, but because the universe itself may prevent us from looking any farther. This is the great mystery. The observable universe is not necessarily an edge of existence. It is an edge of information. And those two things are profoundly different. Imagine standing on a ship in the middle of an ocean covered by an enormous fog. You can see only a limited distance. Beyond that distance, the fog hides the horizon. But you would not conclude that the ocean ends exactly where your vision ends. The universe is different because our limitation is not caused by an ordinary fog. It is caused by the finite speed of light, the finite age of the cosmos, and the expansion of space-time itself. The boundary is therefore much more fundamental. It raises a question that sounds almost philosophical, but has a scientific foundation. Can something exist in a way that can never, even in principle, be observed? According to modern physics, the answer may be yes. A galaxy could exist billions or even trillions of light-years beyond our observable horizon. Its stars could be burning. Its planets could be orbiting those stars. Its galaxies could be colliding. Its entire cosmic history could be unfolding. And yet none of the information produced there may ever reach us. From our perspective, that region would be permanently inaccessible. But there is an even stranger possibility. Some of the distant galaxies we observe today may already be beyond our ability to communicate with in the future. We see them because their ancient light is reaching us now. But the light they emit today may never reach Earth. In that sense, the telescope can show us a part of the universe's past that we will never be able to interact with again. The farther into the future the universe evolves, the more severe this isolation could become. If dark energy continues to drive accelerated expansion in roughly the way our current models predict, increasingly distant galaxies will cross beyond our cosmic event horizon. Their light will fade from our future observable universe. Over immense stretches of time, the cosmos visible from Earth could become dramatically emptier. This does not mean those galaxies disappear. They simply become causally disconnected from us. The universe continues. We simply lose access to parts of it. And this creates a profound asymmetry. There may be regions that can observe us while we can no longer observe their future. There may be regions whose ancient light is reaching us now even though their present condition is forever inaccessible. And there may be vast regions that have never had any causal connection with Earth at all. Yet the mystery becomes even deeper when we consider the geometry of the universe. Suppose the universe is infinite. Then beyond every horizon, there could simply be more space without end. More galaxies. More structures. More cosmic evolution. The observable universe would then be a finite bubble of knowledge embedded within an infinite cosmos. But what if the universe is finite? Then the question changes. A finite universe does not necessarily need an edge. Space could have a global geometry in which it closes back on itself. In such a universe, asking what is beyond the universe could be like asking what is north of the North Pole. The question assumes there must be something outside when the geometry itself may not allow such an outside to exist. This possibility is difficult to imagine because our brains evolved to understand objects inside space. A room has walls. A planet has a surface. A container has an exterior. But the universe is not necessarily an object sitting inside a larger empty room. Space itself is part of the universe. If the universe includes all physical space, then the phrase outside the universe may not describe a physical location at all. It may simply be a concept that has no corresponding place in reality. And yet, another possibility remains. Perhaps our observable universe is only a tiny region inside a much larger cosmic structure. This is where inflation becomes especially important. If cosmic inflation occurred, it may not have ended everywhere at the same time. Some models suggest that inflation could continue in distant regions while ending locally, producing enormous regions of ordinary expanding universe within a much larger inflating background. This idea is known as eternal inflation. Within some versions of this framework, what we call our universe could be one region, or bubble, among many. Other regions could exist beyond our observable horizon. They might have different histories. They might even have different physical properties. But this is where we must be extremely careful. Eternal inflation is a serious topic in theoretical cosmology. It is not established observational fact. There is currently no direct evidence confirming that other bubble universes exist. The idea emerges from certain inflationary models and from attempts to understand their implications. That distinction matters. A mathematical possibility is not automatically a physical discovery. And this is one of the central challenges of studying what lies beyond the observable universe. The farther we move beyond direct observation, the more dependent we become on theoretical assumptions. We can test some consequences of those theories. We can search for signatures that might indirectly support them. But there is a point where multiple explanations can produce similar observable predictions. And then the question becomes much harder. Imagine, for example, that the universe is enormously larger than what we can observe. From our perspective, the observable region may look extremely uniform. But perhaps that uniformity continues far beyond our horizon. Or perhaps, at sufficiently large scales, the universe eventually changes character. Maybe matter is distributed differently. Maybe the global geometry becomes apparent. Maybe the physical conditions differ. Or perhaps absolutely nothing dramatic happens. Perhaps the simplest answer is the correct one. More of the same universe. That possibility may actually be the most conservative. But even it contains a mystery. If the universe extends vastly beyond what we can observe, how large is it? Cosmological observations place constraints on its geometry and possible minimum size, but they do not currently give us a definitive total size. The universe could be vastly larger than the observable region. How much larger remains uncertain. And if it is infinite, another uncomfortable question appears. If space is infinite and the number of possible arrangements of matter is finite or bounded in some sense, could enormously distant regions eventually repeat patterns? Could there be regions unimaginably far away that resemble our own? Could another galaxy exist with a star system resembling ours? Could there theoretically be another planet with a history resembling Earth's? These ideas arise naturally when discussing infinite cosmological models. But they should not be confused with observations. We have no evidence that an exact duplicate of Earth exists somewhere beyond our horizon. Such conclusions depend on assumptions about infinity, the number of possible physical states, and how matter is distributed across an infinite cosmos. The mathematics can be fascinating. The evidence remains absent. And this brings us to perhaps the most unsettling aspect of the mystery. There may be questions about the universe that are not merely difficult to answer. They may be fundamentally unanswerable. If a region is permanently beyond our causal horizon, no future telescope may reveal it. No spacecraft may reach it. No signal may return from it. No experiment performed here may directly test what is happening there. At that point, science must rely on what can still be inferred from observable consequences. But what if there are no observable consequences? Then two completely different realities could exist beyond our horizon while producing exactly the same observations within it. If that happened, there would be no experiment capable of distinguishing between them. The question would cease to be an empirical question. And this is where cosmology encounters one of its deepest boundaries. Science is extraordinarily powerful. But science does not promise that every question about reality can be answered. It tells us what can be tested, what can be inferred, and where uncertainty begins. The observable universe may therefore be more than a region of space. It may be a boundary around human knowledge itself. And yet, there is something remarkable about that boundary. Even though we cannot see beyond it, the universe we can observe contains clues. The geometry of space. The pattern of galaxies. The cosmic microwave background. The expansion history. The behavior of dark energy. All of these may tell us something about the larger cosmos. The great question is whether those clues are enough. Could observations within our horizon reveal the global structure of a universe much larger than our own visible region? Could future measurements uncover subtle evidence of regions we can never directly see? Or are we trapped forever inside a cosmic bubble of observable reality, unable to determine what exists beyond it? The answer may depend on discoveries that have not yet been made. And that is where the most extraordinary possibilities begin. Because if the universe is larger than what we can observe, there may be more than one way to explain its hidden extent. Some possibilities require nothing more than an enormous continuation of ordinary space. Others emerge from inflation, quantum physics, or unconventional ideas about the geometry of reality. And although none of these possibilities has been confirmed as the final answer, they offer radically different visions of what could lie beyond the cosmic horizon. To explore them, we must now enter the most speculative territory of all. Not to confuse imagination with evidence, but to ask which possibilities are supported by physics, which remain mathematical possibilities, and which may forever remain beyond the reach of observation. If we cannot directly observe what lies beyond the observable universe, then how can we even begin to describe the possibilities? The answer is by following the physics we know, extending it carefully beyond the limits of direct observation, and then asking what different models of the universe would predict. Some possibilities are relatively conservative. Others are radically speculative. And the crucial distinction is not between ideas that sound ordinary and ideas that sound extraordinary. It is between ideas supported by evidence, ideas that remain plausible but unconfirmed, and ideas for which we currently have little or no empirical support. The first possibility is also the simplest. There may simply be more universe. More space. More galaxies. More dark matter. More cosmic voids. More of the same physical reality that surrounds us. If the universe continues far beyond our observable horizon and remains statistically similar on sufficiently large scales, then there is nothing mysterious about what lies beyond it in a local sense. The mystery would simply be one of scale. The observable universe would be like a small window into a much larger cosmos. This possibility is strongly compatible with what we currently observe. The large-scale universe appears remarkably uniform. The laws of physics appear consistent across enormous distances. And the cosmic microwave background shows that the early universe was extraordinarily homogeneous on large scales. None of this proves that the entire universe is uniform forever. But it makes a simple continuation of the observed universe a reasonable expectation. The second possibility is more subtle. The universe could be finite but without an edge. This may sound impossible at first. If something is finite, shouldn't it have a boundary? Not necessarily. Consider the surface of Earth. It has a finite area, yet if you walk across its surface, you never encounter an edge where the ground suddenly stops. You can continue traveling. You eventually return to where you began. Now imagine a similar idea extended into 3 dimensions. The geometry would be far more difficult to visualize, but mathematically it is possible for space to have a finite total volume without possessing a physical boundary. In such a universe, asking what lies beyond the universe would be fundamentally different from asking what lies beyond a wall. There may be no external region at all. Space itself could be globally closed. However, observations indicate that the geometry of our observable universe is extremely close to flat. That makes strongly curved finite geometries less favored by current measurements, although the relationship between local curvature, global topology, and total size is more complicated than simply saying to flat means infinite. A universe could have very little measurable curvature and still possess a non-trivial global topology. So the possibility remains open. Another possibility comes from the theory of cosmic inflation. Inflation proposes that the very early universe underwent a period of extremely rapid expansion. One of the remarkable consequences of inflation is that a tiny initial region could have expanded to an enormous size. If inflation occurred in a way that continued beyond the region that eventually became our observable universe, then the total universe could be vastly larger than what we see. Our entire observable cosmos could represent only a tiny fraction of the region produced by inflation. In this picture, the part of the universe we can observe is not special because it is the whole universe. It is special only because it is the region from which information has been able to reach us. But some versions of inflation lead to something even more dramatic. Eternal inflation. In certain theoretical models, inflation does not end everywhere. Instead, it continues in some regions while ending in others. Where inflation ends, regions of ordinary expanding universe can form. If this process continues indefinitely, the result could be an enormous, perhaps continually expanding structure containing many separate regions. These regions are sometimes described as bubble universes. Our observable universe could be inside one such region. Other bubble regions could exist far beyond our observable horizon. Some versions of these models even allow different bubbles to have different physical conditions. Perhaps the values of certain fundamental constants could vary. Perhaps the particle content could differ. Perhaps entirely different low-energy physics could emerge. This is an extraordinary possibility. But it comes with an equally important warning. There is no direct observational confirmation that other bubble universes exist. Eternal inflation is a theoretical consequence of certain inflationary scenarios, not an established observation. Scientists have investigated whether collisions between hypothetical bubble universes could leave detectable signatures in the cosmic microwave background. So far, there is no confirmed evidence requiring such an explanation. This is an important lesson about cosmology. A theory can be mathematically sophisticated, physically motivated, and scientifically interesting without being experimentally confirmed. Another possibility arises from the multiverse. The word itself can mean different things depending on the model. In some contexts, it refers to the bubble universes associated with eternal inflation. In others, it can refer to completely different mathematical frameworks, including interpretations of quantum mechanics or theories involving different possible vacuum states. These ideas are often grouped together in popular discussions, but they are not one single scientific theory. They make different assumptions and have different implications. And some may not currently be testable. That is why saying the multiverse exists would go far beyond what the evidence allows. At present, the multiverse remains a broad family of speculative possibilities rather than an established component of observational cosmology. Then there is another possibility that sounds simpler but is perhaps more profound. Maybe the universe is infinite. If space extends without end, then there is no final boundary waiting somewhere beyond the observable horizon. There is simply more space. Forever. In such a universe, the observable cosmos would be an unimaginably small portion of the whole. This possibility is compatible with a spatially flat universe, and current observations are consistent with near-flat geometry. But even here, an important question remains. Can we prove that the universe is infinite? Not with our current observations. We can measure the geometry of the observable universe. We can place limits on its curvature. We can estimate how large it must be compared with the region we can observe. But demonstrating actual infinity would require information about the universe on scales beyond our observational reach. And there is another possibility that becomes especially interesting when we consider quantum physics. Perhaps our current description of spacetime is incomplete. General relativity works extraordinarily well on cosmic scales. Quantum mechanics works extraordinarily well at microscopic scales. But combining them into a complete theory of quantum gravity remains one of the major unsolved problems in physics. We do not yet know what spacetime fundamentally becomes under extreme conditions. And if our understanding of spacetime itself changes at the deepest level, then our assumptions about cosmic horizons could eventually require revision. This does not mean that quantum gravity automatically reveals another universe. It does not. It simply means that our current theories may not represent the final description of reality. Some speculative approaches to quantum gravity, string theory, and related frameworks suggest additional dimensions or more complex structures underlying the spacetime we experience. If extra dimensions exist, they could potentially change how we think about the universe's geometry. But once again, these possibilities remain theoretical. There is currently no established observational evidence demonstrating that additional spatial dimensions provide the explanation for what lies beyond the observable universe. And perhaps the most radical possibility is one that sounds almost trivial. Maybe there is nothing beyond it. But this statement needs to be handled carefully. If by nothing we mean empty space beyond the observable universe, that is not really nothing. Empty space is still part of the universe. It has geometry. It can expand. It can contain fields and vacuum energy. So if the observable universe were somehow the entirety of physical existence, there would not necessarily be a dark region sitting outside it. There would simply be no outside. The universe would be all there is. This is why the phrase, "what is beyond the universe," may contain a hidden assumption. It assumes that the universe is an object located inside a larger environment. Modern cosmology does not require that picture. The universe may instead be the totality of physical spacetime. In that case, asking what lies outside it may be like asking what exists beyond the boundary of space itself. The question may not have a physical answer. And yet, there is one final possibility worth considering. Perhaps the observable universe is not merely limited by distance. Perhaps our entire observable region is one part of a much larger structure whose properties vary on scales so enormous that we have never detected those variations. If that were true, then our assumption of cosmic uniformity could eventually break down. The universe might contain structures far larger than the largest structures we currently observe. However, there are limits to how large coherent structures can reasonably become under standard cosmological models. The universe's large-scale distribution appears statistically homogeneous, and observations place strong constraints on violations of that principle. So while enormous structures can exist, claims of increasingly gigantic cosmic structures must be evaluated carefully against the underlying statistics and cosmological models. This brings us to an important conclusion. There is no single scientifically established theory describing what lies beyond the observable universe. Instead, we have a hierarchy of possibilities. The most conservative is that the universe simply continues beyond our horizon. Another possibility is that it is finite but without an edge. Inflation allows the observable universe to be a tiny region of a much larger cosmos. Some inflationary models lead to eternal inflation and possible bubble universes. Other theoretical frameworks explore additional dimensions or deeper structures of spacetime. And some possibilities may ultimately prove impossible to test directly. The evidence does not currently tell us which one is correct. But there is something remarkable about all of this. The mystery does not arise because science knows almost nothing about the universe. It arises because science knows so much that we can precisely identify where observation ends. We know the universe has a finite age. We know light has a finite speed. We know spacetime expands. We know the expansion is accelerating. And we know that these facts create horizons beyond which information may never reach us. The boundary is therefore not a failure of our imagination. It is built into the physics. And that leaves us with a final question. If the universe contains regions that may forever remain beyond our direct observation, what can humanity realistically hope to discover about them? Could future observations reveal indirect evidence of a larger cosmic structure? Could new measurements of the cosmic microwave background, gravitational waves, dark energy, or the geometry of spacetime expose clues that today's instruments cannot detect? Or will the observable universe remain an eternal boundary around everything we can ever know? The answer may already be hidden in the faintest signals reaching us from the early cosmos. And if we learn how to read those signals with greater precision, we may discover that the universe has been telling us something about its hidden extent all along. Perhaps the most unsettling thing about the universe is not how much we can see. It is how much may exist beyond our sight. For thousands of years, humanity looked into the night sky and imagined that the stars represented the limits of creation. Then we discovered that the stars were suns. We discovered that the Milky Way was a galaxy. We discovered that there were countless other galaxies beyond it. And eventually, we discovered something even more profound. The universe itself is expanding. That discovery transformed the meaning of distance. The farther we look, the further back in time we see. The oldest light we can detect comes from a universe that was radically different from the cosmos surrounding us today. And beyond that ancient light lies a boundary. Not a wall. Not an edge. Not a place where space suddenly ends. A boundary created by the finite speed of light, the age of the universe, and the evolution of spacetime. We call it the observable universe. But the observable universe is not necessarily the whole universe. That distinction may be the most important idea in this entire journey. What we can see is limited. Reality may not be. There could be vastly more space beyond our cosmic horizon. There could be countless galaxies that we will never observe. There could be regions of the universe whose light has not yet reached us. And there may be regions whose light will never reach us at all. If the universe continues far beyond our horizon, then our observable cosmos may be nothing more than one small window into a much larger reality. Perhaps the universe is infinite. Perhaps it is finite but without an edge. Perhaps inflation created a cosmos vastly larger than anything we can see. Perhaps some inflationary models are correct and our observable universe is one region within a much larger structure. Or perhaps our current understanding of spacetime is incomplete, and future physics will force us to rethink what the word universe actually means. At the moment, none of these possibilities has been established as the final answer. And that uncertainty is not a weakness. It is one of the most important principles of science. We distinguish between what has been observed, what can be inferred, and what remains hypothetical. We know the universe is approximately 13.8 billion years old. We know it has expanded from an extremely hot and dense early state. We know the expansion is accelerating. We know the cosmic microwave background preserves information from the young universe. We know the large-scale cosmos appears remarkably uniform and extremely close to spatially flat within the limits of our observations. But we do not know the total size of the universe. We do not know whether it is infinite. We do not know whether the geometry of the entire cosmos eventually reveals a global structure beyond our observable region. And we have no confirmed evidence that other universes exist beyond our own. Those questions remain open. And perhaps they will remain open for a very long time. Because there is a fundamental difference between discovering something that is merely far away and discovering something that is permanently beyond our causal horizon. If a distant galaxy is simply far away, in principle, we can imagine receiving more information from it. But if cosmic expansion places it beyond our event horizon, then no amount of waiting may allow new information from that region to reach us. Its existence could be real. Its future could be unfolding. And yet, from our perspective, it would remain forever inaccessible. This creates one of the strangest situations imaginable. There may be parts of reality that exist but can never become part of our empirical knowledge. And if that is true, then the observable universe is more than a map of what we can see. It is a map of what we can potentially know. But there is also something deeply inspiring about this limitation. The fact that we cannot see everything does not mean we know nothing. From a single planet orbiting an ordinary star, we have reconstructed the history of the cosmos. We have detected radiation that has traveled for billions of years. We have measured the expansion of space. We have discovered dark matter through its gravitational effects. We have found evidence for dark energy through the accelerated expansion of the universe. We have mapped structures so enormous that their dimensions defy ordinary intuition. And we have learned that the universe we can see is only one chapter in a story that may be vastly larger. Every improvement in our instruments extends that chapter. Every new observation tests the assumptions behind our models. And every unexpected result has the potential to change the story again. That may be the most important lesson of all. The boundary of knowledge is not necessarily the end of discovery. Sometimes, it is where discovery becomes most interesting. Because beyond the observable universe, we encounter a question that no telescope can answer directly. What does reality look like when there is no possible observer from here to see it? Maybe the answer is simple. Maybe beyond our horizon there is simply more universe, extending farther than we could ever comprehend. Maybe there are structures unimaginably distant from us, evolving under the same laws of physics that govern the stars above Earth. Maybe the cosmos is finite, but has no edge. Maybe it is infinite. Maybe our universe is part of something larger. Or maybe some of these questions are fundamentally beyond the reach of observation. We do not know. And for now, that is the honest answer. But there is a strange beauty in it. The universe does not owe us an accessible explanation. It does not have to place every answer within the reach of our telescopes. Yet somehow, from one small world, we have learned enough to recognize the scale of what we do not know. We began by asking what lies beyond the observable universe. Perhaps the most accurate answer is this: we don't know what is there. But we know why we cannot see it. We know that the universe extends beyond the boundary of our observations, or at least, current physics gives us strong reasons to consider that possibility. And we know that the horizon surrounding us is not necessarily a boundary of existence. It is a boundary of information. A boundary created by light, time, and the expanding fabric of space. And somewhere beyond that boundary, whether there is simply more of our universe, an unimaginably vast cosmic structure, or something our current theories cannot yet describe. The story continues. We simply may never be able to see the next chapter. And perhaps that is what makes the universe so extraordinary. Not that we have discovered everything, but that after centuries of looking upward, we have finally learned to recognize just how enormous the unknown really is.